This lecture is about normal subgroups and quotient groups. So just to put this into a familiar context, recall we had the abelian group of integers. And for every positive integer m, the subgroup mz. And we have the congruence classes modulo m, which are the same as the left cosets of the subgroup mz, namely things of the form x plus mz. So this is just a set of integers, everything of the form x plus mk, k and z, or if you like, x plus h for all h in mz. It's all the same thing. And we look at the set of congruence classes. Which is the same as the set of left cosets, z mod mz. And it happens that there are just m of them. And we were able to define addition of these cosets, x plus mz plus y plus mz. The sum of these two congruence classes or cosets is the congruence class or coset x plus y plus mz. And with this addition, z mod mz is a group. So in this very important case, we have a group Z, a subgroup of multiples of m. We look at the left cosets, which are the congruence classes. We could define an addition of congruence classes. And with that addition, Z mod mz is a group. That means that this operation of addition of the cosets is well defined, it's associative, there's an identity element, and every element has an inverse. So we would like to generalize this to subgroups of an arbitrary group. Let H be a subgroup of the group G. So consider G mod H, which is the set of all left cosets. So we would like to be able to multiply cosets by the following rule. If you take the coset xh, now I'm writing things multiplicatively because we're proving things about general groups, and the coset yh, I would like the product to be the coset xyh. So this has to be well defined. It means it's independent of what representative of the coset you choose. And then it has to be associative, there has to be an identity, and there has to be an inverse. And so we would like to be able to do this, but it's not always possible. So this is not possible for every subgroup of a group. So it's not possible for every subgroup of a group. But it is possible for what are called normal subgroups. And the definition of a normal subgroup is the following. A subgroup H of G is normal if you take it the left coset XH, and if you take the right coset HX, if these are equal for all elements in the group. So if your coset has if your subgroup has the property that every left coset is a right coset, then you have what is called a normal subgroup, and multiplication is possible. So let me just show proof that coset multiplication is well defined for normal subgroups. And the proof is really just an exercise in associativity. If I take the coset XH and I multiply it by the coset YH, so we have associativity for multiplication of subsets of a group. So this is the same as X times H times YH, just by associativity, which is X times HY times H. But if H is normal, HY is the same as YH. And this is the same as Y times H times H. But when you multiply a subgroup by itself, you just get the subgroup. So this is XYH. So this set equals this set, and it doesn't matter what representative of the set you choose. This set times this set is this set. So that's a proof that if you have a normal subgroup, coset multiplication makes sense. And of course, you can say, well, when do you have a normal subgroup? Well, in an abelian group, XH equals HX for all X and G and H and H, true for all X and H in the group. And so your left coset is always equal to your right coset. So therefore, every subgroup of an abelian group is normal. Which means we can define multiplication in the set of left cosets. So then we get the big theorem. If H is a normal subgroup of the group G, then G mod H is also a group. And G mod H is called the quotient group. So the proof that this is this is a group follows right away from the fact that G is a group. So let's prove associativity. Associative, get to spell it right. Associativity. associativity. For all elements x, y, z in the group, if we multiply xh times yh, and then multiply that by zh, what we have in here is xyh, which we're multiplying by zh. So that's xy times zh. But because multiplication in the group is associative, this element is the same as xyzh, which is the product of xh and xyh, and yzh, which is the product of xh and this, which is yh times zh. So that proves associativity. What is the identity? Well, if you take the coset EH, which is just the set H, for all x in the group, xh times EH is xEH is xh, and EH xh is EXH equals 8xh. So therefore, this is the identity coset. And finally, existence of inverses. Well, if you take the coset xh times the coset x inverse h, you get x inverse h, which is h. And similarly, x inverse h, xh equals x inverse xh, which is h. So therefore, if you take this coset and multiply it by this, you get the identity. So the inverse of the coset xh is the coset x inverse h. So we just proved that for a normal subgroup where this coset multiplication is well defined, the set of left cosets become a group, and it is called the quotient group. I mentioned that every subgroup of an abelian group is normal. And a consequence of that is every quotient group of an abelian group is normal. Sorry, not normal, is abelian. And the proof is very simple. If you take any two cosets, G mod H, so if you multiply them, you get the coset xyh. But xy is the same as yxh, which is yh xh. So that shows that the quotient is abelian. We can make some other very nice observations. For example, every subgroup of index 2 is a normal subgroup. So recall the index of a subgroup H in the group G is the number of left cosets. And that's also equal to the number of right cosets. So what does that mean? Suppose we have a subgroup of index 2. Here's the group H. If you take any element of the group G, which is not an H, so X is in G, but not in H. So if I take the coset XH, that's different from H, because X is in one, but not the other. And there are only two cosets, so that has to be equal to the whole group. But similarly, if I take X, H, and I take the right coset, these two are different, and there are only two right cosets. So these are also equal to the group. So the left coset XH is G with H removed, but that's also the same as the right coset HX. So if you take any subgroup of index 2, that's always a normal subgroup. And the quotient group will have, of course, cardinality too. Can make one other observation. If G is a finite group, then by Lagrange's theorem, so H, that's H being a normal subgroup. So and if H is a normal subgroup, then if I take the quotient group, the cardinality of that is the order of G divided by the order of H. So, but again, this is just an immediate consequence of Lagrange's theorem. Right? The order of a subgroup divides the order of the group, and more than that, the order of the group is the order of the subgroup times the number of cosets, which in the case of a normal subgroup is the cardinality or the size of the quotient group. What is a nice example of a subgroup of index 2? So suppose we take the symmetric group S3, which has 6 elements. There's the identity, the 3 cycle 1, 2, 3, the 3 cycle 1, 3, 2, and the 3 transpositions 1, 2, 1, 3, and 2, 3. Suppose we let H be the set consisting of the identity and the 2, 3 cycles 1, 2, 3, and 1, 3, 3, 2. This is a subgroup of index 2. And G mod H consists of 2 cosets H and, well, let's say 1, 2 times H. I can just choose any element that's not an H. So this other coset really consists of the 3 transpositions. So this is the quotient group of a group. It's a very important construction, and you really need to spend as much time as you can understanding the construction and looking at examples and doing homework problems.